Next we will see the limitations of the Williamson synthesis. Now we understood Williamson synthesis. Now what is the limitation? The first point is that in case of Williamson synthesis, if you want to prepare, that is tertiary ether or secondary ether, don't take tertiary alkyl halide or secondary alkyl halide. Why? Because it will not undergo substitution reaction, it will undergo elimination reaction. Again I repeat, if you want to prepare tertiary ether, then don't take tertiary alkyl halide or secondary alkyl halide, it will undergo elimination reaction instead of substitution reactions. It will undergo. Alright, that means here alkene will be the major product instead of ether. You will be getting ether, no doubt, but ether will be minor product. Minor means hardly 5 to 10%, and alkene will be around 85 to 90%. Then why to do the reaction then? Alright, so see here how it is we are getting it. See CH3, C here CH3, and here I am just this one I am taking it CH3 and Br, let us say, plus CH3ONA. Isn't it? Same Williamson synthesis, but I have taken here tertiary alkyl halide. What I said, we should not take this. It will give you what? Alkenes. How? Now look here. Here Br will take a pair of electrons because Br is more electronegative than carbon. Got it? It will take a pair of electrons. So what you find is that it forms a tertiary carbocation as a result. When Br is going to take a pair of electron from here, then it becomes a tertiary carbocation. Now tertiary carbocation is what you can say quite stable in nature, you know that. Alright. So but it cannot remain in the cationic form, isn't it? It's not stable. Alright. Tertiary carbocation is stable compared to what? Compared to secondary, compared to primary, compared to methyl. On basis of that comparison, it is being stable. But what you can say, ions are not stable, isn't it? It cannot remain in this equation in the ionic state. Clear? It has to become a stable reaction. We have to get a product, a stable product. So hence, moreover, this carbon is having 3 bonds because this bond goes, this pair of electron goes. It is taken by bromine. So it is having 3 bonds, we can say, which is not possible. So as a result, this pair of electron comes here. Either this or this. This is known as alpha hydrogen. It comes here. This pair of electron, and it forms H plus here. Br minus H plus. Br minus H plus. Now, next you see what is happening. Here CH3O minus and Na plus. Now this Na plus reacts with this Br minus because metal has strong affinity for halogens. Alright, they have got strong affinity for halogens to form what? NaBr. Clear? And as you can see it here, this goes, Na plus goes with Br minus to form NaBr. This H plus goes with CH3O, alright, to form CH3O minus to form what? That is nothing but CH3OH. And what is being left, you see here? What is being left? You are getting CH3, CH3, here what is that? Double bond, CH2, isn't it? CH3, CH3, double bond, CH2. See here? This pair of electron goes, so it's CH2, here CH3, CH3, so double bond CH2. What are you getting? Alkenes. That's it what I said. Don't take tertiary alkyl halide, then you will get alkene as a major product. You will get alkene as a major product instead of getting ether. Now the question is, then what should I do? What should I do? If I want to prepare tertiary ether, then what should I do? No problem. I will be taking here tertiary sodium alkoxide. Instead of tertiary alkyl halide, what I need to do? I need to take tertiary sodium alkoxide, and the alkyl halide is primary. Previously, I took the sodium alkoxide as primary and the alkyl halide I took it as tertiary. Here, instead of that, the sodium alkoxide I took it as tertiary and this as primary. Then what is the product you will be getting it? The product is, now see, very simple. So what is that? This here is O minus, Na plus, Br minus, CH3 plus. Now you can say very clearly, isn't it? Na plus goes with Br minus to form what? NaBr plus, what are you getting it? CH3, C, CH3, CH3 here at the bottom, and now O negative goes with this positive to form what? OCH3. Understood? If you want to prepare tertiary ether, don't take tertiary alkyl halide, but you take tertiary sodium alkoxide. This is known as tertiary sodium butoxide because 4 carbon atom is there. So butoxide. Again I repeat, tertiary sodium butoxide. I am writing it here. Tertiary sodium butoxide. Alright, and this is your methyl bromide will give you, that is nothing but a tertiary ether, you are getting it. That is nothing but here, what is this name of this compound? The name of this compound is, what is that? 2,2-dimethyl methoxyethane. Isn't it? 2,2-dimethyl. See here, in the second position, first position, 1, 2. So, 2 dimethyls are there. The 2,2-dimethyl methoxyethane, 2 carbon, eth, that's it. It's in this way. So, we are getting it. Now, next is, if you want to prepare, that is aromatic ether, if you want to prepare it, then what you need to do? Same thing. I am going to take ONA plus CH3Br, let us say, or CH3Cl or C2H5Cl, anything, whatever you want, you can take it. So, what you will get it? You tell me, what you will get it? Benzene ring OCH3, isn't it? Why? Same thing, same thing. Br negative, CH3 positive. Benzene ring O negative and Na positive. So Na goes with Br to form what? NaBr. Positive, negative. And benzene ring O goes with CH3 to form benzene ring O CH3. What is this? This is nothing but methoxybenzene or anisole. Alright, methoxybenzene or anisole. Here also same thing. If you want to prepare an aromatic ether, don't take tertiary alkyl halide. Take primary alkyl halide. Don't take tertiary alkyl halide. Why? It undergoes elimination reactions. To give you alkene, it will give you. Alright, understood now? So, in this way, you can prepare, that is ether. The main, what you can say, limitations of this Williamson synthesis is that to prepare, that is aromatic ether, to prepare tertiary ether, you need to take primary alkyl halide. Alright, you need to take primary alkyl halide, because if you take secondary or tertiary alkyl halide, I told you repeatedly, it will not give you ether, it will give you alkene as a major product. You will be getting it. Understood now, Williamson synthesis? Fine. So, next, after that, we will, that is, see, there are some other methods by which you can prepare ether. Other methods. Other methods means, suppose if I take here C2H5Cl and another C2H5Cl. Why I am writing in this way, you will come to know. In presence of Ag2O dry, when I heat, that is C2H5Cl, 2 molecules of C2H5Cl in presence of Ag2O dry, this should be dry. Alright, then what I am going to get it? See here, what I am going to get it. Why I wrote in this way, you will come to know. What is this? I got 2 Ag and 2 Cl. So what is that? 2 AgCl. And what is being left? Its left is C2H5O C2H5. C2H5O C2H5, you got it. That's it. Now you can take here 2 different halides also, like C2H5Cl, CH3Cl. That also you can make it. So what you will get? C2H5O CH3, no problem. But this should be Ag2O dry. Why? Because if it is Ag2O moist, remember what I said you in alcohol, moist Ag2O means AgOH. Moist Ag2O means AgOH, and AgOH is unstable. I said you that. For that reason we write it here moist Ag2O. And that will give you what? Alcohol. C2H5, 2 molecules will react with AgOH to give you nothing but alcohol, and you will be getting AgCl. Alright now? Clear? So hence I have to write it here dry Ag2O. Because if I write moist, then you will be getting alcohol, not ether. Got it? Fine. Now, next is, you have studied that if you are heating alcohol in presence of 413 Kelvin, isn't it? You have studied this in alcohol chapter. C2H5OH plus H2SO4 conc H2SO4 in 413 Kelvin. Alright, you have studied. What is going to give it to you? It is going to give you C2H5O C2H5 plus water. Why? Because conc sulfuric acid acts as a dehydrating agent. It acts as a dehydrating agent. We have seen the mechanism also in the alcohol chapter. 413 Kelvin. If you take 443 Kelvin, then you will be getting alkenes in 443 Kelvin. Alright, at that time we will not take 2 molecules. We will take 1 molecule of ethyl alcohol. Alright, so in this way you will be getting it. Now, if you want that, no, I will be taking the dehydrating agent something else, like alumina, C2H5OH in presence of alumina, and you will be heating it to around 523 Kelvin. Instead of conc H2SO4 as a dehydrating agent, I am taking alumina. Then what I am going to get it? I am going to get, that is again same thing, two molecules will be getting C2H5O C2H5 plus water. I am going to get it. Here alumina acts as a dehydrating agent. Clear? Now we can also prepare, that is alcohol, by taking some other reagent. Got it? By other method. So what is that? Let us say C2H5O, that is Cl or C2H5OH, I will be taking it, plus CH2NH2. Alright, CH2NH2 if I take. In presence of HbF4, tetrafluoroboric acid, HbF4, which acts as a catalyst. HbF4, tetrafluoroboric acid. Now what is going to happen here? Same thing. O minus, H plus, CH2, that is negative, that is CH2, that is positive, and N is negative. So in this way, what I am going to get it, see, C2H5O negative goes with this positive. Goes with this positive. Alright, clear? To form what? To form, there is nothing but C2H5O CH2. Now plus, what you get it is that, you get it is ammonia. NH2 reacts with H to form ammonia, but this is stable, this particular one. Okay. Now before going to that, let me tell you the name of this compound. This is known as diazomethane. Diazomethane. Alright. Now, CH2N2, it should be CH2N2. So it is known as diazomethane plus N2. Clear? Now this H, where it will go? Clear? Now see here. Diazomethane is CH2N2, that is C2H5OH plus CH2N2 will give you C2H5OCH2, because accordingly O negative goes with this positive, and N2 and H. Now N2H is not stable. It's not stable. For that purpose, what will happen is that, now why it is not stable? Because see, very simple. N2 means N triple bond, and another H means what? It will have 4 bonds. Will it be stable? No. For that purpose, it is not stable. So hence H will be released. Alright. Now when H is released, H takes a pair of electron and hence it becomes negative. So hence it reacts with this positive to form CH3. Alright. What I said? N2 will release an electron, that is, and it is forming H. Now this H, which is negative, reacts with this CH2, which is having deficiency, to form, that is nothing but CH3. Carbon is having deficiency of electron now, because carbon is having 3 bonds. So hence it forms CH3. So hence you get it C2H5O CH3 plus nitrogen. So that is nothing but in this way you can prepare it. Now next is, if you want to prepare higher ethers, higher ethers you like to prepare, then what will you do so? Clear this process? You are getting it? Now higher ethers, if I need to prepare, then what will I do is that I will be taking here, that is CH3, CH2O, CH2Cl, let us say. A chlorinated ether I have taken it here, halogenated ether. You can take anything, Cl or Br or I. Alright, so this is an halogenated ether. What is that the name? Chloroethyl methyl ether. Or we can say, what is the name? Suppose if I am putting it here CH3, what is the name? Methoxyethane, isn't it? Methoxyethane. So instead of H, one Cl is coming. Then what will come? Chloromethoxyethane. So hence IPC name is also same thing in alphabetical order. Chloroethyl methyl ether. Not chloromethyl ethyl. Chloroethyl methyl ether. Alphabetical order. Got it now? Understood? Plus, that is CH3MgCl. I'll take it. Alright, CH3MgCl. What is going to happen here? Same thing. It is nothing but CH3, CH2O, CH2 goes with CH3. Plus MgCl is there. It goes with another Cl to form NgCl2. Now why is it? Same thing. Do the charge separation always. Negative. This is positive. Clear? Now this is negative. This is positive. So this positive goes with this negative. Alright, now why it is negative? You know that carbon is more electronegative than magnesium. You studied in lower classes. This thing. Here chlorine is more electronegative than carbon. You also studied in lower classes. So hence this is negative. This goes with Mg positive to form MgCl2 and we get it. So hence what you are getting here? You are getting a higher ether or not? Here this was what? Chloromethoxyethane. What I got? I got ethoxyethane. I got it. So one more carbon atom is added, you can see. Instead of chlorine, one more carbon atom is added. So I get a higher ether. So to convert into higher ether, what you find is that this method is used. That is, if you use here CH3 instead of CH3, if you take C2H5, then what you will get here? C2H5. If you use here C3H7, you will get C3H7 here. Got it? Depending upon this group, this carbon atom is going to increase, and hence the number of carbon atom increases in case of ethers. Alright, accordingly the question it is being asked. So these are the different methods for the preparation of ether, so to say. Thank you very much.